everyone. Glad you could attend. This is a little bit of a follow-up from my session on Tuesday, although I won't be talking about distributed ledger asset taxonomies and things like that. I was actually asked to yesterday to delve into the area of some advanced technologies that obviously have an impact on distributed network data ledgers. So that's what we're going to do today. I know from Tuesday's session, there's not really a Q&A format. However, if there is an audience or viewers that view this as a recording, my contact information is listed here. I'd be happy to take on any questions that you might have, so feel free to reach out. So, in regards to these technologies and with any of the technologies that I ever speak on academically to graduate students or otherwise, I don't talk about any technologies that I've not been formally academically trained in. So my PhDs, master's degrees all fall into these areas of study, which makes them increasingly fascinating current day because I started engaging these technologies back in the early 80s when many would say, oh, that's just the beginning. Well, it's really not, because if we take a look at just a really brief timeline of each of these, we see that the concept of quantum was actually introduced by Planck in 1900. He really developed the idea of energy, and it is wrapped in packets that he termed quanta, which is where we get our quantum physics from. Quanta is Latin. It is the plural form of quantum. So that's where we get the English word quantity, quality. It's looking at this idea of the Latin origin of quanta, which literally means, how much. And then Einstein came along with his idea of photoelectric effect that said, oh, light also travels in packets, packets of energy. And then the principle of uncertainty was really I think the next major breakthrough, where Heisenberg actually took a look at the indeterministic aspect of these quanta, these packets of energy. So we don't have time to delve into that, but understand that the study of quantum mechanics, which led to quantum computing in future years, is anything but new. And then if we take a look, a really brief look at the timeline of artificial intelligence, the whole idea was really birthed by Turing back in the 40s. During his work in World War II and computing and things like that. From a more historical perspective, in the 80s, it was in 1956 that artificial intelligence actually received its name, because John McCarthy, who was at Dartmouth at the time, actually coined the phrase artificial intelligence. And so it was natural language programming and things like that, which is what I was heavily involved in the 80s and even into the 90s and such. And then we see, again, by 2017 is where we got into the transformer architecture. Some might note, and others might know, that OpenAI actually started in 2015. And it was in 2018 when they released their first chat version in the AI model bot environment. And then 2019 was their second release. And of course, their revolutionary release that caught everyone's attention was Chat 3, or Chat GPT, in November of 2022, which included what in architectural engineering as an architectural engineer. Myself is the general pre-trained transformers. That's not an open AI term. That is actually an AI engineering term that they tacked on. And rather than just calling it Chat 3, they called it Chat GPT because of the introduction of transformers in model development in 2017, which they actually acquired the company that formulated that to then go on and become what they are today. And then when we take a look at a brief timeline of data blocks and hash chains, many people think that that began with Satoshi Nakamoto, which again, as I tell many people, I was in a lot of the forums in 2003, the open forums, where the team of Nakamoto was discussing things with developers, things like that. It was a completely open forum. And I had nothing to do, by the way, with the development of Bitcoin. It was just, from my perspective, research and seeing what they were doing, because I'd been involved in data block technology, distributed computing, and cryptography going back to, again, the 80s, following people like Dr. Chom and earlier developers like Leslie Lamport. So just to kind of highlight, my study as an undergrad actually went back to 1949 with Dr. Claude Shannon, who's often considered the father of information theory. And he's actually the one that developed a lot of the early mathematical cryptographic confusion and diffusion algorithms, and hypothesized an internet of computers, having obviously read Turing's work and things like that. So that moved on to then other areas, like in the early 70s, the creation of the modern block ciphers and data blocks from Horst Feisel. And he was with IBM. IBM went on to work with NBS, which was the National Bureau of Security, now NIST, to actually develop what became the DES, the data encryption standard. And we still have AES and DES around today, although AES is the more robust version. And then we get into Leslie Lamport, who's 79 and 81, actually invented hash chains. So we can attribute much of what people refer to as blockchains to the development of this technology going all the way back to 1949, and really culminating around about the time I was entering undergrad in 1981. So all of these people often don't receive the acclaim that they deserve for the technology that Satoshi, the team, used to integrate into what we call the Bitcoin network today. So with that, as we take a look at some of the advanced technologies, AI, machine learning, they are not the same thing. AI is an umbrella. Machine learning is the major technology under that umbrella from which many of the other technologies flow, although not the only one. Internet of Things, again, is very important to billions of connected devices these days. And then quantum computing, which is advancing very rapidly. And I will say that much of that advancement that has accelerated our timeline of reaching a level of what's referred to as QT, time to quantum, kind of like Y2K, lived through that too. But quantum is really being accelerated through the aid of AI, mostly in the area of development of silicon-based chips, which is again advancing the timeline. We're really looking at 3 to 5 years to see the next development in quantum computing. Annealing computing, we're already using annealing quantum computing, and I'll talk a little more about that in a moment. And then just really looking at these systems are very complex. There's large amounts of data, which is why some have hypothesized about how great it would be to integrate distributed network data ledgers, i.e., blockchain, again, which really isn't a technology. It was just something that was contrived as a term in 2014. The term never existed prior to that. So if you hear me refer to it as distributed ledger or distributed network data ledger systems, that's what I'm referring to, just in a more technical format. So some of the advancements that really don't get discussed much that are going to rely heavily on artificial intelligence and quantum computing is the area of robotics, which again, the defense conference in Pennsylvania has been going on this week. Is just, it's amazing what people are doing right out of their dorm rooms. Some of them, it was pretty interesting to see some of the students and what they were trying to do in terms of garner contracts with the federal government in assisting develop systems and even very simplistic matters of supply chain management and things like that, using artificial intelligence, robotics, and things of that nature. I'm not going to focus too much on the cybersecurity side. I'm just going to kind of glance through some of these technologies that a lot of times get ignored, that are actually very much integrated into what we're dealing with today in research and design, especially myself being the CEO of My Key Technologies. We're integrating and converging a lot of these technologies and working with different agencies. So extended reality is another one. A lot of people, AR, VR, are familiar with that, augmented reality and virtual reality. You mix those together and you get what's called mixed reality, hence the mixing aspect. When we combine all three of these, what we get is XR, extended reality. Much of my postdoctoral work in this area resides around AR, VR. And just again, Google glasses or Meta glasses and everything else are kind of a byproduct of that. We're still developing out a lot of the frameworks. Some of the best use of this is in military and training and the medical area, actually. So when we take a look at holography, nobody's really paying attention to that. Proto, if anybody's familiar with Proto, love to hear from you, but especially if you've used it. But if you haven't seen it, you can go out to their website. They have actually developed a communications platform for being able to, and there's several videos on their website, to be able to actually holographically, kind of like Star Wars style, be able to communicate and be live with people. So rather than me being communicated to you through a streaming platform, maybe in future years we'll see each other holography through holography's eyes and be able to be present using a system of holography is the use of lights to project an image. Yeah, like I say, I'm not going to spend too much time here on the cybersecurity side, but understand each of these advanced technologies are very oriented, data heavy, and again, AI is accelerating. Various different AI technologies are accelerating these advanced technologies. Another one, digital twinning in conjunction with extended reality is just phenomenal. Some of the directions we're actually able to go with that, especially in the financial markets. We already have following a couple banks right now on the research and more on the development side, where they're actually twinning accounts of account holders And so what you can basically do is create a dashboard of where you have a digitally twinned uh, system log of transactions and put that up against the actual account. So you with using recursive neural networks, which is kind of a shoot off of deep neural networks, shallow neural networks, things like that. It's hypothesizing what the flow of transactions should be. And when you dashboard that against the actual account activity, how banks are using this is to identify real time or near real time fraud that could potentially be taking place, and they can actually hold a transaction so that before, rather than being reactive like many of the compliance departments are, and this is even happening in the stream of transactions of whether it be on the Bitcoin network, Ethereum network, Solana network, it's always reactive. There was a post out on LinkedIn yesterday that hit my inbox that basically they were someone was talking about the fact that, unless you've got an address for us to work with, we can't really do much from a heuristic analytics perspective. Because, until we get that address as a starting point, we have no way of viewing this network. Well, banks have solved that problem in the banking side of actually being able to do that. And so hopefully my enthusiasm around technology and things like that didn't overshadow an understanding of what I was talking about. But I think you can clearly see how creating a synthetic twinned visual of transactions that should happen versus the identification really predictively is going to be a huge area of fraud detection or intrusion detection, even in the cybersecurity realm, not just the financial markets. So moving on from that, let's jump into quantum computing and computational models. Here again, kind of like I described on Tuesday with distributed networks and data ledger systems, everybody thinks of this sequential linear block data system. And that is so old school. That's like the Edsel. But that's what the Bitcoin network was built on. And to a great degree, Ethereum starting to look a little more like a Frankenstein, but that's what it was originally built on. Many of the platforms use directed acyclic graph, DAG, as their underlying architecture, which gets out of the clunky framework of blocking data to where each transaction becomes its own node and can validate off of those. The point being is that without that understanding of architectural design, you really can't have an appreciation for the technology itself. So diving into quantum a little bit from a computational model, we need to understand the difference between gate-based quantum systems, which is what IBM is really focused on. Annealing is where D-Wave lives. So if you've ever heard of these companies, I'm sure everybody's heard of IBM, maybe not so many. D-Wave. D-Wave is one of the leading companies in quantum development. But D-Wave's annealing quantum is already being used in auto plants by like Ford, HSBC Bank for their treasury portfolio management, and things like that. So annealing quantum computing is actually live. Now, the difference here gets into what's the difference between annealing and gate-based? And that's a great question. We don't have time to go into it, but understand that it's not just a different name for doing the same thing. They are very different technologies in the quantum space that do things very differently. So annealing quantum, just to really highlight the distinction, annealing is more able to run efficiency scenarios. And that's why it's being used in portfolio management and in production scenarios. whereas gate-based quantum is more around cryptanalysis. And running these advanced algorithms that are going to do some pretty phenomenal things. And that's where we're looking out 3 to 5 years before we actually see a more robust system. So I kind of, in the Edsel Ferrari Corvette scenario of looking at architectural structures of what everybody likes to call blockchain. I kind of look at annealing as being like apples. Those are computers for people that just give me an app. I don't want to know how to, how it works under the hood. I don't want to be able to program with it. I just need an electronic device with an application that does what, I'm trying to do. Whereas gate-based is a little more like a PC where I can actually get under the hood, I can program, I can change its programming, I can develop new code and things like that in a much more robust way than you can. So I'm not trying to offend any Apple people out there. Just I get a lot of grad students that try to use Apples when we're coding and things like that, and they constantly break. And it's because of their operating system. And that's what we're really talking about here in this computational model of quantum computing. Adiabatic annealing is a little different version of annealing. And again, D-Wave is in that space. One-way quantum, Google, Microsoft are living in that space. And then the topological quantum computing, again, Microsoft and is in that space along with Nokia. When we take a look at categorization by qubit, physical implementation, so we can actually look at quantum computers two very different ways, kind of like with classical computers. Classical computers, we can look at what kind of chip are they using? Are they using an AMD chip or are they using an Intel chip? Versus their operating system, iOS with Apple versus Linux and things like that. You get the idea, I hope. So we have superconducting quantum computers. We have trapped ion quantum computers. And again, these are the qubit physical implementations. So this is at the qubit level. This is like the chip in classical computing. We have photon quantum computers. We have the neural atom quantum. We have the topological quantum. And then we have the quantum dot or silicon-based systems. And that is where a lot of the focus is at right now. So understanding traditional AI models. We covered quantum. Let's take a look at AI and better understand what's under the hood there. So AI integration in enterprise it really is looking at several different things. A lot of people like to talk about generative AI today without really understanding what generative AI is, but just understand that basically as we move into an agentic environment, that is a lot of specialized AI bots that can begin to take their specialties, talk to each other, and actually generate something that doesn't already exist. Because right now, artificial intelligence already takes what's available by scraping primarily the web pages, the thousands and thousands of web pages that exist, and other things that get fed into it, the PII that you share with different firms and things like that can take all your information and social media, all of these different things get packed into these AI models. So you might have one AI model that scrapes social media, another one that scrapes web, another one that scrapes academia. And so in a generative AI environment, those three specialized models can then begin to generate maybe some new concepts around integrating those three different sources of information. Capabilities and limitations, it's important to understand the strengths and weaknesses of models that are being used. There's dozens and dozens of models apart from the ones that are currently open source. There are many that are being developed by cyber criminals, for instance, to how can I get into a bank account in an unauthorized manner? How can I break their system? Versus when you look at Codex, which everybody likes to call Claude code, but Codex allows individuals to basically create their own AI agent and or their own AI model and call it an agent and do some different things with. So all of these things begin to kind of converge on each other. And then governance and responsibility. This is something that I've been pushing. I push in my book that was released this year. And by Wiley and looking at governance and responsibility and guardrails. And one of the things that I know talking with Dara and BLI, we've had many conversations around the necessity for an SRO, a self-regulatory organization, much like what gets used in the securities area with FINRA, providing the guidance, testing, certification, oversight of the broker-dealer environment, reporting to the SEC and SRO, and that environment is very much needed in these advanced technologies with people that really understand what's going on, not the investors, the venture capitalists, and things like that who, yes, they've got deep pockets when it comes to resources, but they aren't necessarily the people that understand it the best. They have a working idea, obviously throwing money at it, but at the end of the day, it's the technologists, the engineers underneath that know it best. When we look at AI, a lot of people are not familiar with the fact that AI, again, as an umbrella, has a taxonomy. And we can begin breaking this into machine learning or symbolic learning. So we've got a basic taxonomic breakdown here that, as you see, we get deeper and deeper into this, we can begin to see the level of technologies that exist here. So when you think of AI, when people, I love it when people come up and say, "What do you think about AI?" And it's like, which technology under AI are we talking about? Because we can't really speak about it until we understand which one we're dealing with. Because talking about machine learning in general is very different than, well, let's talk about deep neural networks or shallow neural networks or recursive neural networks. They all do something a little different. They all learn different. They have different designs, architectures, models, applications, use cases. So you get the idea. We need to better understand these technologies under the hood so that when we talk about them, we're not just talking generally about them. We can be very specific and get out of this hype mode, because just like with digital assets of the past that got hyped and never fulfilled their fulfilled hype. The same thing to a large extent happened to AI technology and quantum as well. So when we take and break artificial intelligence down into typologies, there's actually a type 1 and type 2. Here again, many people aren't familiar with this, but I'm going to focus on the type 1 because this is where we live today, specifically in the narrow AI, narrow artificial intelligence is what we call stupid AI in the engineering side, architectural side, weak AI if you want to be nice. But basically, this AI is basically just, it's designed to do one thing and it does it well. And that's what chat does. That's what Claude does. Although we are starting to break into that agentic environment that we were talking about earlier, of creating an agentic environment to then jump into generative AI, where AI starts actually creating something that wasn't actually introduced by humans. But that's where we'll talk about in a moment, human intelligence comes into play. And don't confuse generative AI with general AI. So where we are in the progression in the technology is moving from narrow AI. We're just making strides in the general AI, general artificial intelligence area. And that is where an AI model, and we're not there yet, so I can't really describe what it's going to look like, but the conceptual model of general AI or smart AI is where an AI agent actually begins to think for itself. It doesn't need humans anymore. And then super AI, which I love the fact that Meta is constantly out there talking about the fact that they're developing super AI. Well, we're not even past the general AI phase yet. And I have to remind people that, remember, it used to be called Facebook, and they were going to change the world with the metaverse, and spent $28 billion and got nowhere. So, again, a lot of hype around super AI, but that is actually the point where we meet singularity. That, if you're not familiar with the singularity principle, it's where basically the technology becomes smarter than the human. So good luck to Meta. The type two, again, I'm not really going to touch on it here, but much of this is still theoretical. And some of it is getting integrated into robotics to a large extent. But when we take a look at the stage of development, we can kind of see by type. This is the reactive, limited, theory of mind, self-awareness. That's the type two. In robotics, the reactive and limited memory is really kind of current stage, along with, as I stated earlier, artificial narrow intelligence from the type one. Theoretical future stage really is pretty much where everything else falls. This is something that I just introduced as an idea a little bit ago, but I've been integrating this into my teaching for years, and people are just beginning to pay attention to this. Because, as I said, on the advisory boards of a number of artificial companies 10 years ago, this was something that I really only wanted to work with companies in an advisory capacity that understood this concept of human intelligence. And that's just the innate ability for humans to think, learn, and make judgments. On the other side, artificial intelligence are machines that attempt to mimic that. But in the middle, and what a lot of people are missing, is what's called IA, intelligence augmentation. And that's utilizing artificial intelligence technology to enhance human intelligence decision making. And that's where we really need to focus as a design model in the AI space. And I'm going to pick up the pace here a little bit because I know we're running short on time. When we get into the core concepts, artificial intelligence, again, simulating humans, machine learning, I talked about a little bit. Natural language programming has literally been around for decades. That was, back in the 80s where we were living, and NLP has come so far in the last few years. Natural language programming involves speech to text, text to speech, and now we have natural language processing models that actually integrates contextualization into forming words and sentences. That is where the transformer portion of GTP came into play in that really groundbreaking step in advancing NLP. And then agentic, again, I've talked about that already, so I won't dwell on that any further. Some of the capabilities in the generative AI space is computer vision. People laugh when you say that, but it really is a thing. It basically uses deep learning models and convolution neural networks. Things like YOLO, you only look once, vision transformers and clips, contrastive language image pre-training to extract and analyze information from images for generative model image creation. So that is actually a real thing. When you take a look at art and speech synthesis, it's pretty incredible that you can just speak into your device, tell it what you're looking for, and it synthesizes something based on what you said. People, if you haven't been in this technology for the last 40 years like I have, it's it's just amazing what people take for granted today, picking up at this point to not understand how very rudimentary it was 40 years ago. Advanced technology convergence, and this is where we get into the convergence of AI, PQC, QRC, that stands for post-quantum cryptography or quantum resistant cryptography. The two terms get thrown around. That's why I put them together. The idea is much like what I emphasize when people talk about the idea of the chaining of blocks being tamper resistant. The resistant part does not get emphasized enough. And I'm going to do the same thing here because post quantum cryptography, quantum resistance in the engineering side is really the preferred term because we're looking at quantum resistant cryptography. We really don't know what that's going to look like. We're assuming based on models that it is going to be resistant, but there's still a lot of unknowns that as we get non-annealing computers out there that can do cryptanalysis through Schnorr signatures, Grover signature algorithm, and things like that, will we know exactly what they're capable of? So anyway, you get the idea here. Post-quantum cryptography is really just cryptography that is trying to, in a quantum environment, provide a solution because we've not been able to actually develop a quantum cryptography yet. We're still in the phase of classical cryptography. And that takes us to some of the data issues that exist out there. Many people are very concerned about networks like the Bitcoin, Ethereum, Solana. There are some out there that have said some distributed network data ledger environments that say, oh, we've solved that problem. We've introduced post-quantum cryptography and we're all good to go. And yet where they put the cryptography isn't where it's going to matter most. And hopefully we'll get to that exact point here. But we do see production grade AI distributed ledger type systems, especially in the layer 2 arena for enterprise grade architectures. Most of that gets applied to the to the layer 2 contracts, which have no cryptography in them. That's why you don't see any PQC component there. Artificial intelligence is doing more of the work of trying to do transaction monitoring and flow bottleneck monitoring, things like that. When we get to architectural blueprint challenges, so up here we see this DARQ, that's for DLT, artificial intelligence, extended reality, and quantum computing. You may see that term coming up more common. It's fairly common in the research and academic area, DARQ. But that's really where we are at this point. in 2026. That's still yet very much in development in terms of the convergence of all of that. But the challenges around that are very intense, especially in the fact that if you're going to integrate distributed ledger technology into the convergence of artificial intelligence, extended reality with all of its data types, and quantum computing, which it still takes classical computers to talk to a quantum computer. We don't talk to them directly. We talk to them through classical computers. So we're not destroying the classical computer age for anybody that's thinking that. But for distributed ledger technology to really be introduced into this data heavy environment, we really need to have an FHE ZKP type environment, not snarks or starks. Snarks and starks are like super lightweight versions of proofs. And in their name, the A in snarks and the A in starks stands for arguments, not proofs. These are like stripped down versions of ZKP. They're being broken all the time in the layer 2 networks of Ethereum, especially, but in lesser known ones as well. And we also, the context of federated learning. DLT needs to develop more of a federated architectural framework, because as we're integrating all of these different agents, they've got to learn from each other. And so there has to be this integration capability. FHE is still very much future oriented, especially where you're dealing with all types of data types, as we see here in this convergence model. So just be aware of that. The governance, I think I've already delved pretty heavily into that. And then just security systems, zero trust architectures, as emphasized by NIST, that comes up in all of the model designs for user authentication systems and things like that that I've developed with my key, and actually tried to introduce them during my 40 years of working with military special operations and Treasury and cybercrimes headquarters. And it's industry's a little quicker to adopt, but government's really slow, and they're just now catching on. And I'm retired from that now. So now I work from the outside and give them my stuff for a lot more than what it would have cost them a decade ago. All right. So when we look at post-quantum, quantum cryptanalysis, and current day cryptographic ciphers, this is usually the part that a lot of people get intrigued and start asking questions about, because, gee, is quantum computing really going to break all of this stuff? And so classical and modern cryptographic algorithms, this is really a taxonomy of what they look like. When you take a look at some of the more modern, it falls under the RSA area that came out in the 80s. And we're still relying heavily on RSA. Your elliptic curve is over here. Elliptic curve was developed around the same time frame as RSA. So both of them are very, very old schematics. So new cryptographic algorithms have had to be developed, and most of those come, and I'll highlight here in a moment. Quantum decryption threat, again, and that's kind of what's triggering everyone right now. Long-term data risks, that's kind of behind the concept of, you steal the data now and decrypt later. And then just the security paradigm is changing in the environment of quantum threat. One of the most amazing things that I've seen is with the data that's coming in, with a 3 to 5 year time frame to reaching a quantum environment that can execute cryptanalysis being decrypting current cryptographic algorithms. Very few companies have actually taken any steps towards moving in that direction. Um, and it literally, to do a complete data inventory, especially if you're talking about a bank or something like that, takes years to inventory all of your data, prioritize it, and then begin to introduce QRC or PQC algorithms into the process. So people are scared by it, but I guess they're paralyzed. The flight, fright, or freeze theory here is everybody's kind of frozen. When you take a look at the threat of quantum computing, data security risks, Shor's algorithm, this is a very short version of Shor's algorithm, by the way, but you're going to start seeing things like this more and more. And what you see with these little lines and the variables involved are state values of qubits. Kind of fun. For people when they look at that. It's like, what do I do with this? This is Grover's algorithm. Grover's algorithm is not nearly as sophisticated. It can theoretically break AES, but their AES 256 is a little more robust, and government and industry is still using that. So again, just to kind of highlight some of the risks that are there. Some of the modern cryptanalysis myths, breaking them. So a little play on words there, breaking modern cryptanalysis, which is breaking cryptography. Anyway, my little play on words. Deciphering weak keys. People have come out and said, "Oh yeah, we broke RSA." Well, they didn't really. I've seen a few posts over the last few years that there were claims from some European research that they had done that, and it's like, okay, show us the papers. If you're going to put this out on LinkedIn and create this fear factor, put the paper out there. And I've challenged them to do that in post, and none of them have ever done it, because when it really comes out, they're using really small key sizes, 50-bit keys. And I was just talking about AES 256. That's a 256-bit key size. These are just, it's kind of like, giving a problem of what's 2 plus 2 to a mathematician with 3 PhDs in the area of cryptanalysis or in cryptography. It just, it's like, that's not hard. And so these claims are really involved deciphering weak keys. They ignore the difference between physical and logical qubits. So again, we don't have time to go into the difference between physical and logical qubits, but it does make a difference for quantum computers to reliably run algorithms like Shor's that need millions of physical qubits to create a smaller number of stable error-corrected logic qubits in order to break things like RSA, scalable RSA that's used in industry, or elliptic curve cryptography that's used in distributed ledger environments. Hyping flawed quantum algorithms actually has a synonym to a quantum approximate optimization algorithm. So that's where, experts have noted are very misleading. They don't scale effectively to break modern encryption. And then failing to provide verifiable proof, as I was mentioning earlier. When we take a look at some of the post-quantum cryptography, we have lattice-based, stateless-based, code-based, and multivariate. Don't have time to get into the various versions of that, but at least you've seen it. If you haven't seen it before, you're seeing it here, and you can say, oh, you run across, multivariate PQC. Oh yeah, I've seen that someplace, and go do some more research. Learning is a key. Lifelong learning is a key to keeping up with this stuff. There is an alternative to PQC and QRC that was raised in 2022 when NIST jumped on this. It's called ZVC. It's zero vulnerability computing. It's really cool technology. It can be scaled much faster, and it actually gets built into the chip as opposed to being software oriented. And that's something I've been calling for years. But here again, that gives you a nice overview, I hope, of some of these technologies of artificial intelligence, quantum computing, and the like to give you more familiarity with it. Are we able to take any questions, or are there any questions that are are we done with the recording?
Yeah, I think we're good, Dave, unless there's any questions on Jackie's side, but I'm not sure if she's actively on the Zoom, so I think we're good. Thank you for your presentation.
Okay, you're welcome. All right, bye.
Bye. Have a good day.